Electrochemistry. Part 1. Electrolytic conduction and transport number. Electrolytic and metallic conduction and factor affecting them. Electrolytic and metallic conduction. Substances which allow electricity to pass through them are known as conductors, whereas substances which do not allow electricity to pass through them are known as insulators. Conductors are divided into two classes: those which conduct electricity without undergoing any decomposition. These are called electronic conduction conductors. Example: metals, graphites, and certain minerals. As the name indicates, the conduction in this case is due to the flow of electrons. Those which undergo decomposition when current is passed through their aqueous solution or melt. These are known as electrolytic conductors or electrolytes. Example: solutions of acids, bases, and salts in water, fused salts, etc. In this case, the flow of electricity is due to the movement of ions. Electrolytes are further classified into two main categories as strong electrolytes and weak electrolytes. Strong electrolytes are substances like strong acids, example HCl, HNO3, H2SO4, etc. Strong bases, example NaOH and KOH, etc., and most of the inorganic salts. This dissociates almost completely in the aqueous solution or in the molten state and hence conduct electricity to a large extent. Weak electrolytes are substances like weak acids, example CH3COOH, HCN, H2CO3, H3PO4, etc., and weak bases. Example NH4OH, COH twice, AlOH thrice, etc. These have low degree of dissociation and hence conduct electricity to a small extent. Substances like sugar, urea, etc., the solution of which do not conduct electricity, are known as non-electrolytes. Factor affecting electrolytic conduction. The conductance of the solution of an electrolyte depends upon the following factors: interionic attractions, which depend upon the interactions between the ions of the solute and hence are called solute interactions. On the basis, the substances are classified as strong electrolytes and weak electrolytes as already mentioned. Solvation of ions, which depend upon the interaction between the ions of the solute and the molecules of the solvent and hence are called solute-solvent interactions. Then 10% ionized in the aqueous solution. However, there are many electrolytes whose behavior is intermediate between strong and weak electrolyte, that is, the dissociation is less than 100% but greater than 10%, and similarly their conductance is less than that of strong electrolytes but greater than that of weak electrolytes. Such electrolytes they are called moderate or intermediate electrolytes. Example: O-chlorobenzic acid, O-nitrobenzoic acid, and cyanoacetic acid. Viscosity of the solvent, which depends upon the solvent-solvent interactions. The effect of all these factors decreases with increase of temperature, hence the electrolytic conduction increases with increase of temperature. On the other hand, the electrical conduction of the electronic conductors decreases with the increase of temperature. Alternatively, the factors on which the electrolytic conductions depends are as follows: nature of the electrolyte. Strong electrolytes ionize almost completely in the solution and hence conduct electricity to a large extent, whereas weak electrolytes ionize to a small extent and hence conduct electricity also to a small extent. Nature of the solvent. Electrolytes ionize more in a polar solvent, hence greater is the polarity of the solvent. Greater is the ionization, hence greater is the conduction. Concentration of the solution. Higher the concentration of the solution, less is the conduction. This is because in a weak electrolyte the ionization is less, whereas in a strong electrolyte the interionic attractions are high at higher concentration. With dilution, interionic attractions decreases and hence conduction increases. Temperature. On increasing the temperature, the dissociation increases and hence the conduction increases. Difference between metallic conductors and electrolytic conductors. The main points of differences between metallic conductors and electrolytic conductors may be summed up in this table. Metallic conductors. Flow of electricity takes place without the decomposition of the substance. Electrolytic conductors. Flow of electricity take place accompanied by the decomposition of the substance electrolyte. Metallic conductors. Flow of electricity is due to the flow of electrons only, that is, there is no flow of matter. The conductance depends upon the structure and density of the metal and the number of valence electrons per atom. Electrolytic conductors. Flow of electricity is due to the movement of ions, hence there is flow of matter. Metallic conductors. The electrical conduction decreases with increase of temperature. This is because kernels start vibrating, which produce hindrance in the flow of electrons. Electrolytic conductors. The electrical conduction increases with increase of temperature. This is generally due to increase in dissociation or decrease in the interionic attractions. Metallic conductors. The resistance offered by matter is also due to vibrating kernels. The resistance shown by an electrolyte solution is due to factors like interionic attractions, viscosity of solvents, etc. Electrical resistance and conductance. Every substance offers resistance to the flow of electricity to a small or large extent. The law that gives the exact value of the resistance is known as Ohm's law. It states that if two ends of a conductor, a voltage E is applied and a current I flow through it, then the resistance R of the conductor is E by I. Current is generally measured in amperes, whereas voltage is measured in volts. If 1 ampere current flows through a conductor when a voltage of 1 volt is applied to it, the resistance of the conductor is taken as 1 ohm. Thus, according to Ohm law, R is equal to E by I. Ohms is equal to volts per ampere. In terms of SI unit, ohm is equal to kg meter square per S cube A cube. It is seen that like metallic conductors, solution of all electrolytes also obey Ohm law. It is obvious that a substance which offers greater resistance will allow less electricity to flow through them. This result also follows the Ohm's law, according to which I is inversely proportional to 1 by R. The reciprocal of the electrical resistance is called the conductance. It is usually represented by C. The C is equal to 1 by R. It is a common practice to speak of the conductance of a solution rather than its resistance. Units. The units of conductance are Siemens or reciprocal ohms, written as ohm inverse or mho. For example, if a solution has a resistance of 10 ohm, it is said to have a conductance of 1 by 10 ohm inverse or 1 by 10 mhos or 1 by 10 ohm inverse or 1 by 10 Siemens. Specific equivalent and molar conductivities, conductances and relations among them. Specific conductance or specific conductivity, or simply called conductivity. It is observed that resistance R of a conductor is directly proportional to its length of the conductor and inversely proportional to its area of cross section, where P is a constant of proportionality and specific resistance or resistivity. Its value depend upon the material of the conductors. The reciprocal of resistivity is known as specific conductivity or simply conductivity. It is denoted by kappa. Thus, if K is the specific conductivity and C is the conductance of the solution, then R is equal to 1 by C and rho is equal to 1 by K. 1 by C is equal to 1 by K into 1 by A. K is equal to C L by A. Now, if L is equal to 1 centimeter and A is equal to 1 square centimeter, then K is equal to C. Hence, specific conductance or specific conductivity, or simply called conductivity of a solution, is defined as the conductance of a solution of 1 centimeter length and having 1 square centimeter as the area of cross section. Alternatively, it may be defined as conductance of 1 centimeter cube of the solution of the electrolyte, or in terms of SI base units, it is defined as the conductance of 1 meter of the conductor. If the volume of the solution is V centimeter cube, the specific conductance of such a solution at this dilution V is written as Kv. Similarly, at concentration C, it is represented as kappa C. Units. Resistivity. Ohm centimeter. Specific conductance 1 Siemens centimeter inverse. Equivalence conductance or equivalent conductivity. For comparing the conductances of the solution of different electrolytes, it is essential that the volumes of the solutions should be same and they must contain such definite amounts of the electrolytes which give ions carrying the same total charge. The best choice is therefore to consider the solutions having equal volumes and containing their corresponding gram equivalent mass. The conductance of such a solution is called its equivalent conductance. Hence, equivalent conductance of a solution at a dilution V is defined as the conductance of all the ions produced from 1 gram equivalent of the electrolyte dissolved in V centimeter cube of the solution when the distance between the electrodes is 1 centimeter and the area of the electrodes is so large that whole of the solution is contained between them. It is represented by lambda EQ. Relationship between equivalent conductance and specific conductance. The equivalent conductance of a solution is usually not found directly but is calculated from the specific conductance. The relationship between equivalent conductance and the specific conductance may be defined as follows. Consider a rectangular vessel with its two opposite walls 1 centimeter apart and made of some metal sheet so that these act as the electrodes. Case 1. Suppose 1 centimeter cube of the solution containing 1 gram equivalent of the electrolyte is taken in the vessel. The conductance of this solution will be then its specific conductance. Further, if 1 centimeter cube of the solution taken contains 1 gram equivalent of the electrolyte, the conductance of the solution will be equivalent conductance. Thus, when 1 centimeter cube of the solution containing 1 gram equivalent of the electrolyte is considered, the equivalent conductance is equal to the specific conductance. Molar conductance for molar conductivity. The molar conductance of a solution is defined in a manner similar to that of the equivalent conductance as under. The molar conductance of a solution at a dilution V is the conductance of all the ions produced from 1 mole of the electrolyte dissolved in V centimeter cube of the solution when the electrodes are 1 centimeter apart and the area of the electrodes is so large that the whole of the solution is contained between them. It is usually represented by kappa m. Relationship between molar conductance and specific conductance. As in the case of equivalent conductance, the molar conductance is related to the specific conductance as follows. Lambda m is equal to kV into V. Relationship between molar conductance and specific conductance. As in the case of equivalent conductance, the molar conductance is related to the specific conductance as follows. Lambda m is equal to kV into V. Lambda m is equal to kc into 1000 by C is equal to kc into 1000 by molarity, where K is the specific conductance and V is the volume of the solution containing 1 mole of the electrolyte and C is the molar concentration, that is mole-liter inverse. Comparing with the equivalent conductance, the unit of lambda m will be ohm inverse centimeter square mole inverse or Simon centimeter square mole inverse or ohm inverse centimeter square mole inverse. Measurement of electrolytic conductance and specific conductance, equivalent conductance and molar conductance. Electrolytic conductance. The conductance is the reciprocal of the resistance, hence the conductance can be obtained by the principle of Wheatstone bridge method. It consists of 4 arms containing the resistance R1, R2, R3 and R4. R1 is the variable resistance, R2 is the unknown resistance when null point is obtained, that is there is no deflection in the galvanometer G. Knowing the values of R1, R3, R4, R2 can be calculated. It's finding the resistance of the solution of an electrolyte. A special type of cell has to be used such that the solution is present between two electrodes. The cell that used is called conductance cell. It is made of Pyrex glass and has two platinum electrodes at a fixed distance apart. The most serious problem in the measurement of the resistance and hence the conductance of the solution of an electrolyte is that if different current is used, it causes electrolysis of the solution. As a result, the concentration of the electrolyte near the electrodes changes and this results in the change in the resistance of the solution. These effects are called polarization effects. To overcome this problem, an alternating current in the audio frequency range of 550 to 5000 cycles per second is used. However, when the alternating current is used, ordinary galvanometer fails to detect the null point. Hence, the galvanometer is replaced by earphone. Further, to minimize the polarization effects, the electrodes are coated with platinum black, that is finally divided platinum deposited on the electrodes electronically. To sum up, three modifications required in the usual Wheatstone-Bridge method are: source of different current is replaced by a source of alternating current, which is either an induction coil or a volume vacuum tube oscillator, which is quieter and gives more symmetrical current. Second, galvanometer is replaced by an earphone. Third, electrodes of the cell are coated freshly with platinum black before use. The completely assembly for the measurement of the electrolytic conduction is: a suitable value of the resistance R is introduced from the standard resistance box, such that when the sliding contact, that is the jockey J, is moved along the stretched wire, the sound in the earphone is reduced to minimum at a point somewhere in the middle of the wire AC, say at the point D. Then, if X is the resistance of the electrolytic solution by Wheatstone-Bridge principle, resistance R by resistance X is equal to resistance of wire AD upon resistance of wire CD is equal to length AD by length CD. Resistance X is equal to resistance R into length CD upon length AD. Thus, knowing the resistance R and the balance point D, the resistance X of the electrolytic solution can be calculated. Then, conductance C is equal to 1 by X is equal to 1 by R length AD upon length CD. Specific conductance, or simply called conductivity, is related to the conductance according to the expression K is equal to C into L by A. But the specific conductance of a solution can be determined by measuring its conductance and the distance L between the electrodes and the area of cross section of each of the electrodes, but it is not convenient to measure L and A accurately. However, for a particular cell, L by A is a constant, and this constant is called cell constant. L by A is equal to cell constant. Specific conductance is equal to conductance into cell constant. Thus, the cell constant of any particular cell can be found by measuring the conductance of a solution whose specific conductance is known. For this purpose, generally specific conductance of KCl solution are used, which are known accurately at different concentrations and temperature. For a few concentration at a temperature of 298 Kelvin, these values are given below. Concentration of KCl solution 1 molar is or 1000 mole meter cube inverse. Conductivity is equal to 0.1113 s centimeter inverse or 11.13 Simon meter inverse. Knowing the value of the cell constant, the specific conductance of the given solution can be determined by measuring its conductance and multiplying the value with the cell constant. Equivalent conductance lambda EQ is related to the specific conductance according to the equation. Lambda EQ is equal to K into 1000 by C EQ is equal to K into 1000 upon normality, where CQ is the concentration of the solution in gram equivalent per liter, that is the normality of the solution. Thus, knowing the normality of the solution and the specific conductance, molar conductance, the molar conductance is related to the specific conductance according to the reaction. Lambda M is equal to kappa into 1000 by centimeter. Concentration is equal to K into 1000 upon molarity, where Cm is the molar concentration. Thus, knowing molar concentration C and the specific conductance K, delta M can be calculated. Conductivity water. For accurate results, the solutions should be prepared in a specifically purified water whose own conductance is very small. Such water is called conductivity water. It is obtained by distilling good distilled water to which a little potassium permanganate has been added. Water of this type has a specific conductivity of about 8 into 10 minus 7 ohm inverse centimeter inverse. Alternatively, to get the resistance of the electrolyte, the resistance of water used for making the solution may be determined and then subtracted from the resistance of the solution. Variation of conductance, specific conductance, equivalent conductance, and molar conductance with dilution. In general, electrolytic conductance as well as the equivalent conductance and molar conductance increase with dilution, whereas the specific conductance of an electrolytic solution decreases with dilution. The reasons for such a behavior are briefly explained below. The conductance of a solution is due to the presence of ions in the solutions. The greater the number of ions, the greater is the conductance. As on dilution, more ions are produced in solution, so the conductance should also increase on dilution. The specific conductance of an electrolyte falls with dilution because through total number of current carrying particles, that is ions, increase with dilutions, but ions present per centimeter cube of the solution becomes less and less on dilution. However, the increase of equivalent and molar conductance on dilution is due to the fact that these are the product of specific conductance and the volume V of the solution containing 1 gram equivalent or 1 mole of the electrolyte, as the decreasing value of specific conductance is more than compensated by the increasing value of V, so the values of lambda EQ and lambda M increase with dilution. Variation of molar conductance with concentration for strong and weak electrolytes. As already mentioned in the beginning of this chapters, there are two types of electrolytes, namely strong electrolytes and weak electrolytes. The variation of molar conductance with concentration or dilution for each of these electrolytes is briefly discussed below. Conductance behavior of strong electrolytes. As discussed later in more detail in section 2.7, the molar conductance of strong electrolyte is found to vary with concentration according to the equation lambda Cm or lambda naught m minus b under root c, where b is the constant depending upon the type of the electrolyte, the nature of the solvent, and the temperature, and delta naught m is the molar conductance at infinite dilution called limiting molar conductance. This equation is called Debye-Huckel-Onsager equation and is found to hold good at low concentrations. Thus, if lambda Cm is plotted against under root c, a linear graph is obtained for low concentration, but it is not linear for higher concentration, in which KCl has been taken as example of a strong electrolyte. Further, the curve obtained for a strong electrolyte showed that there is a small increase in conductance with dilution. This is because the strong electrolyte is completely dissociated in solution, and so that the number of ions remains constant. At higher concentrations, the greater interionic interactions retard the motion of ions, and therefore the conductance falls with increasing concentration. With decreasing concentration, that is with dilution, the ions are far apart and therefore the interionic attractions decreases, due to which the conductance increases with dilution and approaches a maximum limiting value at infinite dilution, designed as lambda naught m or lambda infinity m. Conductance behavior of weak electrolytes. As a weak electrolyte dissociates to a much lesser extent as compared to a strong electrolyte, therefore the conductance of a weak electrolyte is much lower than that of a strong electrolyte at the same concentration, in which acetic acid has been taken as an example of weak electrolyte. Further, the curve obtained for a weak electrolyte shows that there is a very increasing conductance with dilution, especially near infinite dilution. This is because as the concentration of the weak electrolyte is reduced, more of it ionizes, thus increasing conductance with decreasing concentration is due to the increase in the number of ions in the solution. However, it does not reach a limiting value. Further, from the plot shows that it is observed that the plot of for strong electrolyte becomes linear near high dilution, and thus can be extrapolated to zero concentration to get the value of molar conductance at infinite dilution, that is lambda naught m. However, for a weak electrolyte, such as extrapolation is not possible, as it is clear from the graph. For acetic acid, experimentally also, it is not possible to determine that lambda naught m value for a weak electrolyte, as it does not approach a limiting value. The problem was finally solved by Khertrapal, who put forward a law known as Khertrapal's law. Arrhenius theory of ionization. Postulate of Arrhenius theory. To explain a number of phenomena related to electrolytes such as conductance, electrolysis, anomalous behavior of electrolytes towards colligative properties, that is higher values of osmotic pressures, elevation in boiling points, depression in freezing point, and lowering of vapor pressures than expected, Arrhenius in 1887 put forward a theory about the electrolytes. This theory is known as Arrhenius theory of electrolytic dissociation. The main point of this theory are: an electrolyte, when dissolved in water, splits or dissociates into positively or negatively charged particles called ions. The process is called ionization, or more correctly, electrolytic dissociation. NaCl dissociates as Na positive plus Cl negative, MgCl2 dissociated as Mg2 positive plus 2Cl negative. The total charge carried by the positive ions is equal to that carried by the negative ions, so that the solution as a whole is electrically neutral. On electrolysis, the positive ions migrate towards cathode and hence are called cations, while the negative ions migrate towards the anode and are therefore called anions. The ions formed constantly reunite to form the undissociated molecules till ultimately there is an equilibrium between the ions and the undissociated molecules. In other words, the whole of the electrolyte may not dissociate into ions. Instead, only a part of the electrolyte may dissociate into ions. The fraction of the total number of molecules of the electrolyte that dissociates into ions is called degree of ionization or degree of dissociation. It is usually denoted by alpha. That is, degree of dissociation is equal to number of molecules dissociated upon total number of molecules taken. The degree of dissociation increases with dilution and becomes maximum at the infinite dilution. The conductance of an electrolytic solution is due to the ions produced by the dissociation of the electrolytes. Greater the dissociation, the higher is the conductance. Substances like mineral acids, alkalis, and most of the salts which shows a higher conductance is due to the fact that they possess high degree of dissociation. That is, their molecules are almost completely dissociated into ions in the aqueous solution. Such substances are called strong electrolytes. On the other hand, substances like NH4OH or CaOH twice, which shows poor conductance, is due to the fact that they possess low degree of dissociation. That is, they are only partially dissolved in the aqueous solution. Such substances are called weak electrolytes. The ions produced by the dissociation of an electrolyte behaves like molecules towards colligative properties. For example, each NaCl molecule dissociates to give two ions, that is Na positive and Cl negative. Hence, the observed value of any colligative property is double than the expected value. The properties of an electrolyte are the properties of its ion. For example, the properties of an acid are due to the H positive ions furnished by it in the aqueous solution. Similarly, the properties of a base are due to the OH negative ions produced in the aqueous solution. Evidence in favor of Arrhenius theories. The direct evidence for the Arrhenius theory came from the X-ray studies, which is showed that the solid substances which behaved as strong electrolytes existed in the ionic form and not in the molecule form. Example, NaC is found to exist as Na positive Cl negative. Further, Arrhenius theory is able to explain a number of facts and phenomena related to electrolytes which tend to support to the theory. A few of these phenomena are briefly explained below. Electrolytic conductance. It has been explored in postulate 6 of the Arrhenius theory that the conductance of the solution of an electrolyte is due to the presence of the ion produced by the electrolyte on dissociation. Strong electrolytes possess high degree of dissociation and hence show greater conductance, whereas weak electrolytes dissociate to a small extent and hence show low conductance. Variation of conductance with dilution. It is observed that the specific conductance decreases, whereas conductance as well as equivalent conductance increase with dilutions. The explanation is evidently based on the postulate 5 and 6 of the Arrhenius theory. The equivalent conductance and the dissociation of the electrolyte vary in such a similar manner with dilution that the degree of dissociation of an electrolyte at any concentration can be expressed in terms of equivalent conductance as lambda C upon lambda naught, where lambda C is the equivalent conductance at the given concentration and lambda naught is the equivalent conductance at infinite dilution. Electrolysis. According to postulate 1 of the Arrhenius theory, an electrolyte when dissolved in water dissociates into ions. Thus, the function of the electricity is only to direct the ions towards the electrodes. Colligative properties. The reason for the anomalous results observed about the colligative properties for the solution of electrolyte has already been given in the postulate 6 of the Arrhenius theory. Colligative properties. The reason for the quantitative explanation of the anomalous results about colligative properties of the strong electrolyte was given by Van 't Hoff. He introduced a factor I called Van 't Hoff factor, defined the expression I is equal to observed value of the colligative properties upon normal value of the colligative properties. The factor I could be determined experimentally by dividing the observed value of a colligative property, that is osmotic pressure, lowering of vapor pressure, elevation in boiling point or depression in freezing point with that of the solution of a normal substance like sucrose having the same molar concentration. The Van 't Hoff factor I could be used to find the degree of dissociation as follows. For electrolytes of the type AB, suppose we start with 1 mole of the electrolyte and alpha is the degree of dissociation. Then we have number of moles before dissociation for AB is equal to 1 and for A positive and B negative is equal to 0. Number of moles after dissociation for AB is equal to 1 minus alpha and for A positive and B negative is equal to alpha. Total number of moles after dissociation is equal to 1 minus alpha plus alpha is equal to 1 plus alpha. Assuming normal behavior, that is if there were no dissociation, number of moles would have been is equal to 1, since the value of colligative property is proportional to the number of particles, which in turn is directly proportional to the number of moles. Van 't Hoff factor I would be given by I is equal to 1 plus alpha by 1, so that alpha is equal to I minus 1. For electrolytes of the type AB2, example BaCl2, MgCl2, etc., starting with 1 mole of the electrolyte and assuming that alpha is the degree of dissociation. Initial number of moles for AB2 is equal to 1 and for A2 positive and 2B negative is equal to 0. For number of moles after dissociation for AB2 is equal to 1 minus alpha and for A2 positive and 2B negative is equal to alpha and 2 alpha respectively. The number of moles after dissociation is equal to 1 minus alpha plus 2 alpha is equal to 1 plus 2 alpha. Hence, as in the earlier case, I is equal to 1 plus 2 alpha upon 1 or 2 alpha is equal to I minus 1 or alpha is equal to I minus 1 upon 2. The values of alpha found from these measurements and those found from the expression lambda is equal to lambda c upon lambda no were found to be in a fair agreement with each other for a number of electrolytes. This lent a greater support to the Arrhenius theory. In general, for an electrolyte of the type AXBY, we have number of moles before dissociation AXBY is equal to 1 and XAY positive YBX negative is equal to 0. Number of moles after dissociation for AXBY is equal to 1 minus alpha and for XAY positive X alpha plus and for YBX negative is equal to Y alpha. Then total number of moles after dissociation is equal to 1 minus alpha plus X alpha plus Y alpha. 1 minus alpha plus alpha bracket X plus Y is equal to 1 minus alpha plus alpha dot N 1 plus alpha N minus 1, where N is equal to X plus Y represents the total number of ion produced from the dissociation of one molecule of AXBY. Thus, as before, I is equal to 1 plus alpha N minus 1 upon 1, which gives alpha is equal to I minus 1 upon N minus 1. Ionic nature of reactions. As stated in postulate 7 of the Arrhenius theory, the properties of an electrolyte are the properties of its ion. Thus, the reaction between NaCl solution and AgNO3 solution forming a precipitate of AgCl may be explained as follows. NaCl in aqueous solution ionizes and NaCl gives Na positive Cl negative. AgNO3 ionizes in the aqueous solution as AgNO3 gives Ag positive NO negative 3. When the above two solutions are mixed, we have Na positive plus Cl negative plus Ag positive negative plus NO negative 3 arrow AgCl plus Na positive plus NO negative 3. The reaction between two anionic compounds in aqueous solution taken place in a similar manner. Heat of neutralization. The heat of neutralization is defined as the amount of heat evolved when 1 gram equivalent of the acid is neutralized by the base or 1 gram equivalent of the base is neutralized by the acid. The heat of neutralization of a strong acid with a strong base is always the same, with 13.7 kcal. This is explained by the Arrhenius theory as follows. Suppose the strong acid is HCl and the strong base is NaOH. As both are completely dissociated in the aqueous solutions, the reaction between them may be represented as Na positive plus OH negative plus H positive plus Cl negative gives Na positive Cl negative plus H2O. Because the salt formed, cancelling out the common ions on both sides, the above reactions reduces to H positive plus OH negative gives H2O. Thus, neutralization may be defined simply as the process in which S positive ions given by acid combine with the OH negative ion given by the base to form unionized water molecule. As 1 gram equivalent of any strong acid in aqueous solution gives the same number of H positive ion, and 1 gram equivalent of any strong base gives the same number of OH negative ions. The neutralization involves the combination between the same number of H positive ion and OH negative ions. Hence, the heat of neutralization of a strong acid with a strong base is always the same. If either the acid or the base or both are weak, the heat of neutralization is less than 30.7 kilocalorie. The reason for the lower value is that a weak acid or a weak base dissociates to a small extent, and some heat is used to bring about its dissociation. For example, if the weak acid is acetic acid and the base is NaOH, they dissociate in the aqueous solution as follows: CH3COH equilibrium with CH3COO negative plus H positive. NaOH completely dissociates into Na positive plus OH negative. H positive ions are removed by combination with OH negative ions. The equilibrium shift towards right, that is more of acetic acid dissociate. For acetic acids, the heat of dissociation is 0.4 kilocalorie per mole. Hence, the net heat evolved is 13.7 minus 0.5 or is equal to 13.2 kilocalorie. Similarly, the heat of dissociation of NH4OH is equal to 1.4 kilocalorie per mole, so that the heat of neutralization of NH4OH with HCl is 13.7 minus 1.4 is equal to 12.3 kilocalorie. Salt hydrolysis. It is defined as the process in which the salt reacts with water to give back the acid and base. Salt plus water gives acid and base. Depending upon the relative strength of the acid and the base produced, the resulting solution is acid, basic, or neutral. These observations are also explained on the basis of Arrhenius theory. Ostwald dilution law. According to Arrhenius theory of ionization, when an electrolyte is dissolved in water, there is an equilibrium between the ions and the undissociated molecules. For example, for a binary electrolyte AB, we have AB dissociate into A positive and B negative. Ostwald in 1888 pointed out that the law of chemical equilibrium can be applied to this ionic equilibrium. As a result, he obtained an important relationship known as Ostwald dilution law. Suppose the initial concentration of the binary electrolyte AB in the solution is C mole per liter and alpha is the degree of dissociation. Then we will have initial concentration of AB is equal to C mole per liter, and for A positive and B negative is equal to 0. Concentration at equilibrium C minus C alpha at AB, and for A positive and B negative is equal to C alpha. Applying the law of chemical equilibrium, we get K is equal to concentration of A positive, concentration of B negative upon concentration of AB is equal to C alpha multiply C alpha upon C 1 minus alpha. K is equal to C alpha square 1 minus alpha. The equilibrium constant K for the equilibrium AB dissociate A positive and B negative is called the dissociation constant or ionization constant of the electrolyte AB and may be represented by Kd or Ki. Like any other equilibrium constant, Kd is constant only at constant temperatures. The unit of Kd will be same as those of the concentration C. If the degree of dissociation alpha is very small, as is usually in the case of for weak electrolytes at ordinary concentration, alpha can be neglected in comparison to 1 in the denominator of expressions, then the approximate formula becomes Kd is equal to C alpha square or alpha is equal to Kd by C. Equation 1 and 2 are the two expressions of Ostwald dilution law. Expression 2 can be expressed in word as follows. For a weak binary electrolyte with a small degree of dissociation, the degree of dissociation is inversely proportional to the square root of the initial mole concentration. Further, as C is the concentration in moles per liter, therefore the volume V of the solution containing 1 mole of the electrolyte will be 1 by C liter. Putting 1 by C is equal to V, the expression 1 and 2 can also be written as Kd is equal to alpha square upon 1 minus alpha into V. Alpha is equal to under root KdV, where V is the volume of the solution in liter containing 1 mole of the solute. The Stewart dilution law may be defined as follows. For a weak binary electrolyte with a small degree of dissociation, the degree of dissociation is directly proportional to the square root of volume in liters containing 1 mole of the electrolyte. Validity of Ostwald dilution law. To test the validity of Ostwald dilution law, that is to verify the law experimentally, the degree of dissociation alpha was determined from conductance measurement using the formula alpha is equal to lambda C upon lambda naught at different concentration for a number of electrolytes. For each electrolyte, the data were fitted in equation 1 to see whether the value of Kd comes out to the constant or not. It was observed that the value of Kd comes out to be constant only for weak electrolytes, and that too when the concentration of the solution is not too high, that is for dilution solution only. The value of Kd does not come out to be constant for strong electrolytes, thus it may be concluded that Ostwald dilution law is valid only for weak electrolytes in dilution solutions, thus that is why it contains the dilution law, and it does not hold good for strong electrolytes. As an example, the result of a weak electrolyte, namely acetic acid, and those of a strong electrolyte, namely KCl. Limitations of Arrhenius theory. No doubt Arrhenius theory was able to explain a number of facts and phenomena, but soon a number of objections were raised against this theory, especially when applied to strong electrolytes. A few of these objections are as follows. Arrhenius suggested that ionization of the electrolyte take place when dissolved in water. However, X-ray studies shows that many such electrolytes are already in the ionized state, and the word ionization has been replaced by the word dissociation. Second, as an electrolyte can conduct electricity even in the molten state, it shows that the dissociation of the electrolyte takes place even in the molten state. As such, the function of water could not explain the Arrhenius theory. In other words, it could not explain why the dissociation takes place at all. The most serious objection against the Arrhenius theory was its utter failure when applied to strong electrolyte. Example: Ostwald dilution law, which is derived on the basis of Arrhenius theory using the concept of ionic equilibrium, fails for the strong electrolyte, that is, the constant value of the dissociation constant K is not obtained. B. The degree of dissociation alpha of strong electrolyte calculated from conductance measurement alpha is equal to delta C upon delta naught was found to be different from the calculated from colligative properties. The values were found to be nearly same only for univalent electrolytes. C. Strong electrolytes are almost completely dissociated even at moderate concentrations, that is, alpha is equal to 1 or 100% at all concentrations. Hence, Arrhenius' view that conductance increases with dilution because the dissociation increases does not make any sense. In case of strong electrolytes, the increasing conductance with the dilution must be therefore due to some other factors called interionic effect discussed in the next sections. The ratio lambda C upon lambda naught is therefore better called apparent degree of dissociation or conductance ratio only. The failure of Ostwald dilution law for the strong electrolyte is evidently because of two reasons. Firstly, strong electrolytes are almost completely dissociated in the solutions, therefore the question of equilibrium does not arise. Secondly, the calculation of lambda from delta C upon delta naught is not faulty. Explanation of the anomalous behavior of strong electrolyte interionic effects. D. By Huckel theory. The increase of equivalent conductance with dilution in case of weak electrolytes can be easily explained on the basis of Arrhenius theory, which suggests that the conductance increase because of the dissociation of the weak electrolytes increases with dilution. However, in case of strong electrolytes, as they are almost completely dissociated even at the moderate concentration, the increase in equivalent or molar conductance with dilution must be due to some other factors. The qualitative explanation put forward is as follows. The conductance of the solution of an electrolyte depends not only upon the number of ions but also upon their speed. In case of weak electrolytes, the increasing conductance with dilution is due to the increase in the dissociation of the electrolyte, that is due to the increase in the number of ions. The speed of ions in that the distance between them is quite large, so that there is no interference in the movement of ions by other ions. However, in case of strong electrolytes, the number of ions produced on dissociation is so large that the freedom of movement of ion is hindered by other ions present around it. When the solution is diluted, the ionic interference decreases and hence ionic speed increases, and so does the equivalent or molar conductance. The first successful attempt to explain the variation of equivalent or molar conductance of strong electrolytes with dilution quantitatively was made by Debye-Huckel. The fundamental idea underlying their work is that because of electrical attractions among the positively charged ion, each ion is surrounded by a large number of positively charged ions, which may be represented as an ionic atmosphere of opposite charge, and this affects the speed of the ions in the electric field. The electrical attractions among the positively charged ions which affect the speed of an ion in the electric field are called inter-ionic effects. There are two such effects which are briefly described below. Relaxation effect or asymmetry effect. In the solution, each ion is surrounded by an ionic atmosphere of opposite charge. So long as no electric field is applied, the ionic atmosphere remains symmetrical around the central ions. However, when a current is passed through the solution, the central ions move towards the positively charged electron as it is moving out of the ionic atmosphere. It has to rebuild an ionic atmosphere of positive charge around it, and the old ionic atmosphere dies out. However, neither the destruction of the old ionic atmosphere nor the formation of the new ionic atmosphere take place instantaneously. Each of them takes some time, called the time of relaxations. During this time, the old ionic atmosphere pulls the moving ions backward, hence retards its motion. Hence, this effect is called relaxation effect. Alternatively, it may be argued that as the central ions move, the symmetry of the ionic atmosphere is lost. More ions of the ionic atmosphere are left behind than are present on the front. The excess of the ionic atmosphere present behind the moving ion drag the ion backward and retard its motion. Thus, the effect arises because of the asymmetry of the ionic atmosphere or moving ion, and is called asymmetry effect. Electrophoretic effect. When EMF is applied, the central ions moves in one direction and the positively charged ionic atmosphere moves in the opposite direction. As this ionic atmosphere moves, the solvent molecule associated with it also move along with it. Thus, the flow of the ionic atmosphere and that of the solvent molecule attached to it take place in a direction opposite to that of the movement of the central ion. In other words, the central ion is moving against the stream, hence its motion is retarded. The effect is called electrophoretic effect since it is similar to that opposing the movement of colliding particles in an electric field. Besides the above two facts, the third retarding factor is the normal frictions resistance offered by the medium, which depends on the viscosity of the medium, its dielectric constant, etc. Based upon the above ideas, Debye and Huckel derived a mathematical expression for the variation of conductance with concentrations. This equation was further improved by Onsager, and now the equation is known as Debye-Huckel-Onsager equation, or simply Onsager equation for a univalent electrolyte. It is rewritten in the form delta Cm is equal to delta naught m minus bracket 82.4 above divided dt whole bracket 1 by 2 n plus 8.20 into 10 to the power 5 upon dt 3 by 2 lambda naught m bracket close root c. Here delta Cm is equal to molar conductance at concentration C. Delta naught m is equal to molar conductance at infinite dilution. D is equal to dielectric constant and the medium. N is equal to coefficient of viscosity of the medium. T is equal to temperature of the solution in degrees absolute. C is equal to concentration of the solution, and C is the concentration of the solution in moles per liter. As D and N are constant for a particular solvent, therefore at constant temperatures, the above equations can be rewritten in the form lambda Cm is equal to lambda naught m minus bracket A plus B lambda naught m bracket close under root C, where A and B are constant for a particular solvent at a particular temperature. Verification of the Onsager equation. Two tests can be readily performed to verify the Onsager equations. These are: first, the plot of lambda Cm versus under root C should be linear. Second, the slope of the line should be equal to A plus B lambda naught m calculated by substituting the value of various constants directly. The plots lambda Cm versus under root C for some common univalent electrolytes dissolved in water at 25 degrees Celsius. These lines represent theoretical slopes, whereas small circles represents the experimentally observed points. Thus, the agreement is very fair. In case of certain salts like NaCl, KCl, it is observed that the agreement is excellent at low concentrations, but at appreciable concentrations, the major conductances are somewhat higher than those calculated from Onsager equations. It is probably because there may be some other retarding forces which have been neglected. Thus, the anomaly of strong electrolytes is not yet fully resolved. From equation 2, it may be seen that at infinite dilution, that is when C is approx 0, lambda Cm it becomes equal to lambda naught m expected. Significance of d by Huckel theory. The significance of d by Huckel theory obviously lies in the fact that it is able to explain why the molar conductance of a strong electrolyte at any concentration lambda Cm is less than the limiting value of lambda naught m at infinite dilution in spite of the complete ionization of the strong electrolyte. Migration of the ions and the transport number. Migration of ions. When electricity is passed through the solution of an electrolyte, the ions present in solutions are liberated at the electrodes, that is, electrolysis occurs. These movements of ions towards the positively charged electrodes is called migration of ions. That ions actually exist independently and move with the passage of current in solution towards the positively charged electrodes. Take a U-tip, fill its lower portion by CuCr2O7 jelly obtained by mixing a 5% of solution agar-agar and a mixture of CuSO4 and potassium chromate and allow it to set. The jelly is green in color. To mark the position of jelly, some charcoal is scattered over the green jelly. Our charcoal in both the lanes is added KNO3 solution in agar-agar, that is KNO3 jelly, and then aqueous solution of KNO3. When current is passed, blue colored CO2 positive ions are seen moving towards negative electrodes and yellow colored Cr2O2 negative 7s are seen moving towards positive electrodes. After some time, the two types of ions are seen moving with well-defined boundaries. The experiment clearly shows the migration of ions. Migration velocity of ions and change in concentration Hittov's theoretical device. According to the Faraday's second law of electrolysis, when the same quantity of electricity is passed through solution of different electrolytes, the ions are always liberated in equivalent amounts. This, however, does not necessarily mean that the ions move with the same speed. It may be illustrated as follows. Consider a cell containing the solution and provided with the anode A and the cathode C. Let the solution lying between the electrodes A and C be divided into three compartments, the anodic, the middle, and the cathodic. With the help of the imaginary porous partitions A and C dotted lines. Before electrolysis, suppose there are 13 pair of ions. Positive signs indicated the cation and the negative sign the anions for being present in each of the anodic and cathodic department. F5 in the middle. Now the following different cases may be considered. Case 1, when only anions move. Let two anions leave cathodic compartment and enter anodic compartment. We get the position 2. All the cations have not moved to still we see that the number of ions liberated is the same at both the electrolytes, but we see that the concentration in anodic chamber has not altered while that in cathodic chamber has fallen by 2 molecules. Similarly, we can show that if cations are capable of movement and two of them enter cathodic compartment from anodic compartment, then there will be a fall in concentration of two molecules in the anodic chamber. Thus, we see that the velocity of an ion is proportional to the fall of concentration of chamber from where it leaves. Case second, when cations and anions move at the same rate. Let us assume that two cations move from anodic compartment to the cathodic compartment and two anions move from the cathodic compartment to the anodic compartment. Then we get position 3. In this case, there is a fall in concentration of two molecules in each compartment, but we find that the number of ions liberated at both the electrodes is the same, that is 4. Case 3. When cations moves at double the speed of the anions. Suppose that two cations from anodic compartment leave and enter the cathodic compartment. Since the speed of anions is half with the speed of cations, therefore only one anion enters the anodic compartment. The position is shown in 4. We also observed that the falling concentration in anodic and cathodic compartments are 2 and 1 molecules respectively. The number of the ions discharged is again the same, with 3 on each electrodes. Conclusion. From the above illustrations, we draw the following conclusions. Falling concentration around any electrode directly proportional to the speed of the ions moving away from it. It means falling concentration around cathode is directly proportional to the speed of an ion, and falling concentration around anode is directly proportional to the speed of the cations. Falling concentration around anode upon falling concentration around cathode is equal to speed of cation upon speed of anion. Second, irrespective of the speeds of the ions, the number of ions liberated on both the electrodes is equal. Instead of number of ions, we can speak of the number of gram equivalent of the ion deposited on the electrodes depending upon the number of Faradays of electrically passed. Case 4. When the electrodes are attackable. The above relationship has been derived on the assumption that the ions do not react with the electrodes, but in the silver voltmeter containing silver nitrate solution and having silver electrode, each nitrate ions that reaches the anodic compartment react with the silver of the electrode forming AgNO3, and instead of decrease there is an increase of concentration in the anodic compartment. In a silver voltmeter, the above three cases are shown again. It is seen that in every case there is always an increase in concentration in the anodic compartment. This increase in concentration takes place even when the Ag positive ions migrate from the anodic compartment to the cathodic compartment. In order to find the increasing concentrations that would have taken place if no Ag positive ions had migrated from the anodic compartment to the cathodic compartment, a silver or a copper voltmeter, also called coulometer, is placed in series. Suppose the number of gram equivalent of silver or copper deposited in this voltmeter is X. Obviously, X gram equivalent would have been the increase in the concentration of anodic compartment if no Ag positive ions had migrated from this compartment. However, the actual increase is less due to migration of Ag positive ions. Suppose the actual increase in the concentration of Ag in the anodic compartment is Y gram equivalent. Hence, falling concentration in the anodic compartment due to migration of Ag positive ion is equal to X minus Y gram equivalent. Falling concentration around cathode, increase in concentration around anode is equal to Y gram equivalents. Thus, the speed ratio in this case will be given by speed of Ag positive ions upon speed of nitrate ions is equal to X minus Y upon Y. Transport number. When an electric current is passed, the ion migrates towards the electrodes, thus the electric current is carried by ions. Each ion carries a definite fraction of the total current depending upon its speed. The fraction of the total current carried by an ion is called a transport number or transference number or Hittorf's number. Greater the speed of the ion, greater the amount of current it will carry with it, and hence greater will be its transport number. Let UA and UC be the speed of the anion and the cation respectively. Current carried by the anion is directly proportional to the speed of anion is equal to KUA. Current carried by cation is directly proportional to the speed of cation is equal to KUC. Since current is carried only by ions, total current carried is equal to current carried by anions plus current carried by cations, means KUA plus KUC is equal to K common bracket UA plus UC. Total transient number of anion is equal to Na is equal to KUA upon K bracket UA plus UC. Na is equal to UA upon UA plus UC. Similarly, transport number of the cations will be Nc is equal to Uc upon Ua plus Uc. Two important relations. Na plus Nc is equal to Ua upon Ua plus Uc plus Uc upon Ua plus Uc is equal to Ua plus Uc upon Ua plus Uc is equal to 1, or Na plus Nc is equal to 1. That is, sum of transport numbers of anions and cations of an electrolyte is always unity, thus no current is lost in any other function and the whole of the current is carried by the ions. Second, Na is equal to Ua upon Ua plus Uc is equal to 1 upon 1 plus Uc upon Ua is equal to 1 upon 1 plus R, where R is equal to Uc upon Ua, speed ratio of the cation to the anion. Similarly, Nc is equal to Uc upon Ua plus Uc is equal to Uc upon Ua bracket upon 1 plus Uc upon Ua, or Nc is equal to R upon 1 plus R. Determination of transport numbers. There are a number of methods for the determination of transport number, that is Hitov method, Lodge moving boundary method, third EMF method. Out of these, the first two methods are described below. Hitov's method. Principle. This method is based upon the principle that the falling concentration around an electrode is proportional to the speed of the ions moving away from it. Falling concentration around cathode upon falling concentration around anode is equal to speed of anions upon speed of cations is equal to UA upon UC. Adding 1 to both sides, we get 1 plus falling concentration around cathode upon falling concentration around anode is equal to UA upon UC plus 1, or falling concentration around anode plus falling concentration around cathode upon falling concentration around anode, UA plus UC upon UC, or total falling concentration around both the electrode above falling concentration around cathode, so UA plus UC by UC, or falling concentration around anode upon total falling concentration around both the electrode is equal to UC upon UA plus UC is equal to NC. If the concentration are expressed in terms of gram equivalents, the above expressions may be written as Nc is equal to number of gram equivalent lost from the anodic compartment upon number of gram equivalent lost from both the compartments. It may be seen that the number of gram equivalent lost from both the compartments is equal to the number of gram equivalent discharged on each electrode. Thus, in turn, can be found by placing a silver or a copper voltmeter in series, as according to Faraday's second law. When the same quantity of electricity flows through the silver or a copper voltmeter, the same number of gram equivalent of Ag or Cu will be deposited. Thus, the above formula reduces to Nc is equal to number of gram equivalents lost from the anodic compartment upon number of gram equivalents deposited in the voltmeter. Thus, the determination of the transport number of the cation involves the determination of the number of gram equivalents lost from the anodic compartment and the number of gram equivalent of Ag or Cu deposited in the voltmeter placed in series with the apparatus. However, it is important to note that the above result is applicable only when the electrons are not attacked by the ions. If the electrons are attacked, the result is calculated in a different manner, as discussed in the calculation at the end of this section. To determine the transport number of the anion, there is no need to find the loss in concentration of the cathodic department, because Na can be calculated directly from the equation Na is equal to 1 minus Nc. Apparatus. Evidently, the apparatus should be such that it should consist of 3 compartments, namely as anodic, the cathodic, and the central compartment. Second, the solution of these 3 compartments should not mix with each other on electrolysis. Third, it should be possible to take out the solution of any compartment without disturbing the solution of other compartments. The above requirements are met in the apparatus shown in figure. It consists of a U-tube joined on its 2 sides or 2 vertical bulb glass tubes. All the 3, that is the U-tube and the 2 vertical tubes, have the stopcocks at their bottom. The U-tube is also provided with 2 stopcocks, one on either side at the top, so as to cut off the various compartments from each other when required. In the 2 vertical tubes are placed the anode and the cathode separately. These are of platinum. It is desired that these should not be attacked by the ions. Alternatively, the anode and the cathode of silver or copper are depending upon whether the transport number of Ag positive and ions or Cu2 positive ions is to be determined, in which case the anode is attacked or by the anions. The apparatus is connected to a silver copper voltmeter, also called coulometer, in series with the apparatus together with a battery, a rheostat, a key, or a milliammeter. Procedure. The apparatus is filled with the solution of the electrolyte. The transport number of whose ion is to be determined. A silver or copper voltmeter is placed in series with the apparatus and the various connections as shown in figure. Before electrolysis, the concentration of the electrolyte is found by titrating a KMnO4 in titrating a known weight of the solution against a suitable reagent, against KSC and solution for AgNO3 solution, against hypo solution for CuSO4 solution, after adding Ki into it. Now, a current of 0.01 to 0.02 ampere is passed for 2 to 3 hours. A low current is used so that the change in concentration around the electrodes is not too high, as otherwise the diffusion may take place. After electrolysis, the solution from the anodic compartment is taken out, weighed, and then titrated as before to know the amount of the electrolyte present. The weight of the silver deposited in the silver voltammeter or that of copper in case of copper voltammeter is used is also determined. The solution from the central compartment is also taken out and titrated to see that there is no change in concentration within the experimental errors. In case a change in concentration is observed, the experiment is repeated. It is important to know that in these measurements, the weight of the solution are taken instead of the volumes. This is necessary because after electrolysis, the density of the solution changes and so does the volume. Calculations. The method of calculation may be illustrated by taking the example of HgNO3 as the electrolyte and using silver voltammeter in series. Case 1. When the electrodes are not attacked, that is when platinum electrodes are used after electrolysis. Suppose weight of the anodic solution taken out is equal to W1 gram. Weight of AgNO3 found to be present by titration is equal to W2 gram. Weight of the water present is equal to W1 minus W2 gram. The W1 minus W2 gram of the water contain W2 gram of AgNO3 after electrolysis in terms of gram equivalents. W2 gram of AgNO3 is equal to W2 by 170 gram equivalent of AgNO3 is equal to W2 upon 170 gram equivalent of Ag is equal to x gram equivalent. Hence we can say that after electrolysis, W1 minus W2 gram of water contain x gram equivalent of Ag. Before electrolysis, suppose W3 gram of the solution contains W4 gram of AgNO3. Weight of water present is equal to W3 minus W4 gram. Thus, W3 minus W4 gram of water contains W4 of AgNO3 before electrolysis. W1 minus W2 of water will contain W4 upon W3 minus 4 into W1 minus W2 gram of AgNO3. W4 upon W3 minus W4 into W1 minus W2 upon 170 gram equivalent of AgNO3. W4 upon W3 minus W4 into W1 minus W2 upon 170 gram equivalent of Ag, and in last is equal to Y gram equivalent. Say when the electrons are not attacked means Y is greater than X fall in the concentration of the anodic compartment. Suppose the weight of silver deposited in the silver voltammeter W gram is equal to W by 108 gram equivalent of Ag is equal to Z gram equivalent. Say transport number of Ag positive ion is equal to fall in concentration around anode in gram equivalents upon amount of Ag deposited in voltammeter in gram equivalent Y minus X upon Z. Transport number of NO negative 3 ions is equal to 1 minus NAg positive. Case 2. When the electrodes are attacked, that when the silver electrodes are used. In this case, as the NO negative 3 ions reaching the anode attack the silver anode, there is increase in the concentration of Ag positive ions in the anodic solution instead of decrease. That is, in this case, we will have X greater than Y. Increasing concentration of the anodic solution means X minus Y. Thus, increase in the concentration take place in spite of this migration of Ag positive ions from the anodic compartment to the cathodic compartment. If no Ag positive ions had migrated from the anodic compartment, the increase in the concentration of Ag positive ions in the anodic compartment would have been higher and equal to Z gram equivalent of Ag, that is the same as the amount deposited in the silver voltammeter. Hence, falling concentration in the anodic solution due to migration of Ag positive ions is equal to Z minus bracket X minus 1 gram equivalent of Ag. Transport number of Ag positive ions is equal to Z minus bracket X minus Y upon Z. Transport number of NO negative 3 ions is equal to 1 minus NaC positive. In case of copper voltammeter is used, the number of gram equivalents of copper deposited in the voltammeter is obtained by dividing the weight of copper deposited by its equivalent mass. Moving boundary method. This method is based upon the fact that the transport number of the cations and the anions are given by Nc is equal to speed of cation upon speed of cation plus speed of anion, and Na is equal to speed of anion upon speed of cation plus speed of anion. Thus, by determining the speeds of the cation and the anion, the transport number can be calculated. The apparatus used is shown in figure. It consists of a long tube mounted vertically and fitted with the platinum electrodes on two sides. The salt Ba under investigation is made into solution and then placed between the solution of two other salt B-A and Ba-, one having a common cation and the other having common anion. For example, if Ba is KCl and B-A may be LiCl and Ba- may be CH3COOK, the three solutions are arranged in order of increasing density downwards to avoid mixing effects. The original boundaries are A and B. Even if the solutions are colorless, the boundaries can be observed because of the differences in the refractive indices of the solution. In order that the boundaries may remain sharp throughout the experiment, B- and A- must have smaller velocities than B and A respectively, so that B dash does not overtake B and A dash does not overtake A, then the current is passed. The boundaries move to A dash and B dash. The speed of the cation is directly proportional to length A dash and speed of the anion is directly proportional to length B dash. Hence NC is equal to A dash upon A dash plus B dash and NA is equal to BB dash upon AA plus dash plus BB dash. Factors on which transport number depends. It has been stated earlier that the transport number of an ion is directly proportional to the speed of ion, which in turn depend upon a number of factors. Example, nature of the ion. Normally, the smaller the size of the ion, greater is its speed and hence higher the transport number. For example, the transport number of H positive ion is 0.1 and HCl is greater than that of Na positive ion in 0.1 NaCl or K positive ion in 0.1 NaKCl, etc. Nature of the other ions present. For example, the transport number of Cl negative ion in HCl is different from that of Cl negative ion in NaCl. This may be explained as follows. NCl negative in HCl is equal to UCl negative upon UH positive plus UCl negative. NCl negative in NaCl is equal to UCl negative upon UNA positive plus UCl negative, where UH positive, UNA negative and UCl negative represents the speed of H positive ion, Na positive and Cl negative ions respectively in their respective solutions. As Na positive ion is larger in size than H positive ion, UH positive greater than UNA positive. As a result, the denominator of expression 1 is greater than that of expression 2, and hence NCl negative in HCl is smaller than NCl negative in NaCl, as the numerator is same in both the cases. Hydration of the ions. The speed of an ion and hence its transport number is very much affected by the hydration of the ions. For example, Li positive ions are smaller in size than Na positive ions and hence may be expected to have higher transport number than Na positive ion, but the actual positive is otherwise. This is because the Li positive ions are more hydrated than Na positive ions. Similarly, Na positive ions have a smaller transport number than K positive ions. Concentrations. The transport number of an ion changes with concentrations, but the change is very small. However, in case the increase in concentration result into the formation of a complex ion, the solution falls from 0.444 in 0.005 m solution to 0.003 in 0.025 solution. At still higher concentrations, the transport number appear to be 0 or even negative. This is explained on the basis of the formation of the complex CDI2 negative 4 ions at higher concentration. In dilute solutions, there are few CDI2 negative 4 ions, so that CD2 positive concentration is increased. More and more CDI2 negative 4 ions are formed, which migrate to the anodic compartment. A stage comes when as many CDI2 negative 4 ions migrate into the anodic compartment as the number of CD2 positive ions migrating away from it. So, thus there is no change in the concentration of CD2 positive ions in the anodic compartment, and so the CD2 positive ions appears to have zero transport number. Temperature. As the temperature is increased, the ions tend to approach a transport number value of 0.5. That is, at this temperature, equal fraction of the current is carried by the cations and the anions. In case of ions having transport number less than 0.5 at ordinary temperatures, the transport number increases with the increase of temperature. In case of ions having transport number greater than 0.5 at ordinary temperature, the transport number decreases with the increase of temperature. When the transport numbers of the ions are approximately 0.5 as in KCl, the effect of temperature is very small. Interionic effects. How the speed of the ion is affected by the interionic effect has been discussed in section 2.10 under Debye-Huckel theory. Thank you.